Now that we've looked at how we can use coordinates in 3D spaces and how those are similar to what we see in two-dimensional spaces, we're now going to look more specifically at vectors in three-dimensional spaces. We need to look at vectors in three-dimensional space so that we can describe motion, force, and geometry in that space. The components of a vector are going to track its movement along the x, y, and z axes, and unit vectors are going to encode direction only, just like they do in two-dimensional space. We'll see once again that the ideas that we saw in 2D space expand pretty naturally to three-dimensional vectors. We'll write vectors using similar notation to what we did previously, but we'll have three coordinates, v1, v2, and v3, where v1 is going to represent movement along the x-axis, v2 is movement in the y direction, and v3 is movement in the z direction. The magnitude of the vector follows very simply from the distance formula, where we connect v1, v2, and v3 to the origin 0, 0, 0, and so the magnitude of any vector is just going to be the square root of the sum of the squares of each of its three components. We can look at a slightly different way of representing any given vector by using the idea of standard unit vectors. We have three of those, the vector I, the vector j, and the vector k. I is the vector 1, 0, 0, which means it is a vector of length 1 that extends only in the direction of the x-axis. J is the vector 0, 1, 0, which also has length 1 and extends only in the direction of the y-axis. K then is the vector 0, 0, 1, still of length 1, which is why it's a unit vector, and extending only in the direction of the z-axis. Using I, j, and k then, any vector of the form v1, v2, v3 can be rewritten as the vector that is the sum of the vectors v1 times I plus v2 times j plus v3 times k. Just like every two-dimensional vector had a corresponding unit vector, which has the same direction as the original vector, but has a length of 1, or a magnitude of 1, we can do the same thing in 3 dimensions. So we can describe the unit vector the same way we did in 2 dimensions. We take the vector itself and we divide by its magnitude to create a vector of length 1 with the same direction. Let's put these ideas into practice with a few examples. So here we have the vector v equals 3, negative 4, 12. We want to find its magnitude, and we also want to find its corresponding unit vector. So the magnitude of v, we know that's going to be the square root of each of its components squared. 3 squared plus negative 4 squared plus 12 squared. So that is 9 plus 16 plus 144, which is 25 plus 144 is 169, and the square root of 169 is 13. So this is a vector with magnitude 13. That means that its corresponding unit vector is going to be the vector v divided by 13, which means we divide the components divided by 13. So we get 3/13, negative 4/13, and 12/13. And we can do a very quick check here. The magnitude then of v hat is the square root of 3 over 13 squared plus negative 4 over 13 squared plus 12 over 13 squared. In order for it to actually be a unit vector, its magnitude must be 1. And so we get 9 169ths, 16 169ths, and 144 169ths, which is in fact 1. In this example, we want to find the unit vector in the direction from P to Q. So first, let's actually write the coordinates of the vector PQ. So PQ, we know that that's going to be the vector. Since we're starting at P and ending at Q, we're going to do 4 minus 1, negative 2 minus 2, 5 minus negative 1, which is the vector 3, negative 4, 6. The magnitude of PQ is going to be the square root of 3 squared plus negative 4 squared plus 6 squared. So that's the square root of 9 plus 16 plus 36, which is, doing math in my head, 36 plus 25, 46, 56, 61. Square root of 61. That does not reduce at all. So our unit vector, we'll call it V. We'll give it a little hat to indicate that it's a unit vector. That is going to be PQ divided by the magnitude of PQ, which is going to be the vector 3 divided by the square root of 61, negative 4 divided by the square root of 61, and 6 divided by the square root of 61. Now, I am not bothered by square roots in the denominator, but some mathematicians are, in which case you can rationalize those and rewrite this as 3 square roots of 61 over 61, negative 4 square roots of 61 over 61, and 6 square roots of 61 over 61. All right, in this next example, we have a force of magnitude 20, and we want to write a vector for this force, given that we know it acts in the same direction as the vector 2, negative 1, 2. So what we can do is we can find the unit vector I'm going to call this vector V here. So we're going to do V hat is going to be V divided by the magnitude of V. So let's find the magnitude of V first. The magnitude of V, the magnitude of V is going to be the square root of 2 squared plus negative 1 squared plus 2 squared, which is 4 plus 1 plus 4. So that is 3. So V hat is going to be the vector 2/3, negative 1/3, 2/3. And that's a unit vector. So then our vector F, our force vector, has magnitude 20, and it goes in the same direction as this vector. So we can just multiply that unit vector, which gives us the direction and a magnitude of 1, times 20 to get that our force vector must be 40/3, negative 20/3, 40/3. And remember that we can use this alternate notation and say that this is the vector 40/3 I minus 20/3 J plus 40/3 K. Combining vectors in 3D works exactly the same as it does in 2D. So here we have two vectors u and v, and the first thing we want to do is find 2u plus 3v. So the vector 2u is the one that's twice as long as u. So 2u is going to be the vector negative 4, 10, 2. And 3v is going to be 3 times as long as v, so that's going to be the vector 9, 0, negative 12. And so when we add them, we just add them component-wise, and we get the vector 5, 10, negative 10. Similarly, 5u is going to be the vector negative 10, 25, 5. Negative v is going to be the vector negative 3, 0, positive 4. And when we combine those, 5u minus v, we get the vector negative 13, 25, 9. Last one asks us to actually compute the magnitude of the vector u minus 2v. So minus 2v looks like negative 6, 0, 8. When we combine that with the vector u, which was negative 2, 5, 1, we get that u minus 2v is the vector negative 8, 5, 9. And so the magnitude of that, let me add, be more specific there, the magnitude of that is going to be the square root of negative 8 squared plus 5 squared plus 9 squared, which is the square root of 64, plus 25, plus 81. And we're about to surpass what I can do in my head. 64 plus 25 is 89, plus 81, which is 170. Oh, that probably simplifies to something, but I'm not going to do that. We're just going to leave it as the square root of 170. In our last example, we've got two forces acting on an object, and we want to find a third force so that the object is in equilibrium, so that all three forces add up to 0. So this works the same as it does in two-dimensional space. We know that we want F1 plus F2 plus F3 to equal 0. So let's just let F3 be the vector. We'll call it, A, B, C, just for simplicity. So in other words, we need -6 plus 4 plus A to be 0. Well, that's -2 plus A is 0, so A must be 2. Then for our second component, we need 8 minus 2 plus B to be 0. So B must be -6. And then we need for our last component 2 plus 10 plus C to be 0, so that C is -12. So our third vector is going to be the vector 2, -6, -12. All right, wrapping up what we've learned here. We see that 3D vectors pretty naturally extend all of the 2D ideas we've explored before just by adding on an extra component. So both magnitude and direction are going to be computed the same way they were for two-dimensional vectors. Unit vectors are still going to be used to isolate direction, this time in space rather than in the plane. And we'll see that these three-dimensional tools that we're using or learning are going to be used throughout all of Calculus 3. Taking a peek at what's ahead of us, we're going to learn about something called the dot product. We'll examine how to compute the angles between vectors, and then we're going to look at something called vector projections and how those apply to computing work.